Hi there, everybody. How are you doing? Hope you all are having a good Global Hack Week so far. Just a little bit delayed here because we had an event before at mini events for Wikipedia races. So for those of you who joined for Wikipedia races, hope you enjoyed that one. Let me send a quick announcement to the chat about our workshop while you all fold in. If anybody was here for our first part, give us a message in the chat. Let us know. All right. Let me go ahead and get some of these slides going. You should have them already. Oh, sorry about that. There goes my my charger. Yeah, I think we have them, but we need to go to where we left off last time, which is, I think, slide 32. Yep, hash tables. So yeah, if anybody is there, anyone was from our last workshop, yeah, let us know. I'll tell you, before we get started, I want to make sure that everyone checks in. So let's go ahead and send that check-in link. I'm gonna send it in the chat. It's also available. I'll paste the slide too. Yeah, so I guess we'll go ahead and get started then for this workshop. So hash tables is where we left off in part 1. So we'll go through that. And hash tables store key value pairs. So you could think of in Python a little bit like a dictionary, which we did talk about last time. And they provide fast data retrieval based on keys. So in a sense, you are going to search through the keys if you're using hash table, but you don't have to search through the values. And that's a little bit different than some other data structures where you might have to sift through some large amount of data. Here, you're looking for a specific key, and you can make those keys very efficiently. So let's get on with it with the hash tables and how they work. So a hash function computes an index into an array of buckets or slots. And so the hash function is going to ideally distribute these keys uniformly across the buckets. So the idea is that you can really more efficiently access these keys by distributing them evenly in buckets so that we only have to search, in one bucket, for example, for a key. And collisions can occur when multiple keys hash to the same index. So you do need to make sure that your hash function is set up properly. And that's to avoid those collisions. So here's some collision resolution strategies. There's things like chaining, where each bucket contains a linked list of entries. And, that would be, we did talk about linked lists in part 1, but if you want to know more about linked lists, definitely go watch that again. And also open addressing, where you could find another open slot using techniques like linear probing or double hashing to actually get that open slot and resolve the collision. And there's several hash table use cases. So one of them is implementing associative arrays or dictionaries. Another one is caching mechanisms, where you're trying to cache information from a website or from some data stream that you have. And counting frequencies is another great use case for hash tables, because you can really easily make, like, say, a histogram or access data about frequencies using a hash table. And so we're going to try a problem number 5 here, and it's called first non-repeating character. So here's the problem statement. Given a string S, find the first non-repeating character and return its index. So if it doesn't exist, we'll return -1. So here's some examples down in the bottom. We have an example where this string S is equal to LeetCode. Remember, LeetCode is one of these websites. You can find a lot of these types of problems. And the output would be 0, because the first non-repeating character in the string is L, and L is at position 0 of the string. And then the next example here is AABB. And for that one, the output is -1. So in that case, we're just saying that there is no non-repeating character. A is repeating and B is repeating, so we return -1. So we're going to do some live coding now to actually solve this problem. And yeah, why don't we open up our Visual Studio Code? We did this last time. I'm going to send a link in the chat so that you all can see where to download Visual Studio Code if you don't have it already. And I'm also going to make a code share file for this workshop so that you all can see the code. I'll paste it after we make it so that you'll have access. But there's that code share link. You'll want to save that so that you can also access it. All right. And so, yeah, let's continue on here. I'm going to share my VS Code, this Visual Studio Code window I was talking about earlier. And I'll just delete a bunch of these cells here. So let's get started with it. If we want, we can make the function some memorable name, like first unique characters, or first unique character. And we'll give it some parameter S. And so that S is that string we were mentioning earlier. And what we want to do is create a hash table. And in Python, hash table is called a dictionary object, and we use curly braces to create it. And so let's do a first pass. So on the first pass, we're just going to calculate the count of each character. So, for example, with our AABB example, A would get 2 counts, and so would B. And so we can say for every character in S, we can say the character count And remember, this is a hash table, so we need to give a key. And in fact, we can give the key by using these hard braces. So in the hard braces, we put the key name, which in this case, we'll just use the character itself. And then we'll say character count dot get, and we'll get the character comma 0 from character count underscore count, and we'll add 1. So what are we doing here? We're getting the value of character, and then we're adding 1 to that, and we're reassigning the value at the associated key in the character count hash table. So we're just going to add 1 every time we see the character as we iterate through the string. And now we're going to do a second pass here. And in this second pass, we're going to essentially find the first unique character. And so remember, we've built this table, so now we can check every time we see a character, we can check if it's unique. So let's iterate through in a loop form. And so we have find the first unique character. So for the index, comma, character in enumerate s. Okay, so index will bring us 0, 1, 2, things like that. And character will just be that letter in the string. And if the character count character equals 1, then we will return the index. All right. So yeah, that's going to be how we'll find that first unique character and return its index. And then if we go through both the first and second pass and we never return anything, then we'll return -1, which indicates that we went through everything. We never found any unique character in the whole string. So now we can do some test cases. And first, I'm going to do print first unique character LeetCode. And if I do that, I get 0 because there is a L, just like we said before. And now I'm going to copy this code, and I'm just going to replace LeetCode with love LeetCode. And in that case, now it's 2 because we have 2 L's. And we also have 2 O's from love and code. So the first unique character is this V, which is an index position 2. All right. And so, yeah, let's try one last example where we'll try our AABB example from the slides, and we see that we get -1. So -1 indicates that either character is not unique. All right. So those are our possibilities here. And that is kind of an example of how to use dictionary, because we can really efficiently access these keys. Okay, so yeah, this concludes all of the part 1 datas. Yeah, just any summary, any questions that you might have are welcome. And so I'll just give a recap of the key concepts. Oh, Akshat has a question about the first example, LeetCode. Oh, let's go back to this first example here, because that is a good question. So Akshat asks, for the first example, LeetCode, isn't there 2 E's? There are. So in the problem, we're asking find the first non-repeating character and return its index. So for the first non-repeating character in LeetCode, that would be L, because there is only one L in the whole string. And so we immediately get the first non-repeating character, and we just return 0. Now the E's are definitely repeating. So if it was called eel code, for example, I don't know if there is a website called eel code. That would be kind of a cool website name. But if there was, then actually we expect now to see the index at 2, because the L is unique, and these first E's, you would ignore them because they repeat. So let's see if we get 2. And we do. And so the reason for that is because, again, this first pass is going to calculate that when we access the E character, we found 2 of those when we scanned the whole string. So it would call that, it would not return index, because it would need to satisfy this condition, and it wouldn't because there are 2 E's like you mentioned. So that's a great question. But yeah, so just to recap some of these concepts, we had some arrays and strings where we first started out, and those were great because we learned about how to index data and get some really efficient stuff there. We learned about fixed size arrays, and we learned about immutable strings and the concept of mutability. We did some problems with those. And then linked lists, we then moved on to. We talked about how they can have a dynamic size, and they're super good for inserting and deleting nodes of data. And then we moved on to stacks and queues, where we had 2 different behaviors: last in, first out in the case of a stack, and first in, first out in the case of queues, and how they have some slightly different use cases. And then we did hash tables just now, where we saw that we could quickly retrieve data using keys, because the keys are sorted into buckets using a hash function. So that can be super good. And we learned how to use those. So yeah, let's go ahead. I'm going to paste the first unique character function in the CodeShare. So it's up there now in CodeShare. And feel free to take a look at that if you need it. All right. So yeah, we're going to move on to part 2. Just for a preview here, part 2 is about essential algorithms. So some of the essential algorithms include sorting and searching algorithms. And so we're going to cover both categories. And algorithm efficiency is related to Big O notation. So we're going to talk about Big O notation as well. A lot of people were discussing this in part 1, but maybe you were not familiar with Big O. Now you will be. So yeah, we'll get that going for you. And yeah, why don't we start? But first, I want to have a minute to check in. So just one more time, going to emphasize this. Please check in, and I'm going to actually give you a minute to do this. All right, everybody, that gives us a minute to take a break and check in. So let's start part two. I know you're all excited to start part two. My name is Steven and I work with MLH. I've been working with hackers for quite a long time and doing Global Hack Week actually ever since we started, which was sort of back during the pandemic. So we wanted to make a place for everyone to learn and grow as a community. So yeah, I think we've had a lot of success with that. And so we're going to continue that with this workshop. So today, our goals are to understand the importance of algorithms in problem solving. So we're going to talk about, last time we did some practice problems with data structures and things like that. This time we're actually going to dive in to algorithms, and yeah, we're going to talk about them. And then we're going to learn about their efficiency, which is super important because if you have an algorithm, that might be great, but in computer science, it's almost equally important to have something that's efficient. And if you want, we can then dive into some fundamental sorting and searching algorithms, these so-called essential algorithms. And then we'll engage in some interactive coding exercises so that we can all work together with some of these algorithms and really solidify our understanding. So let's start first with the importance of algorithms. So they really allow us to perform tasks efficiently. It's of course possible to manually sort data, even if you have millions of rows of data. But honestly speaking, it's way better to use algorithms than to do that. And they optimize resource usage like time and memory in the computer to help you out when you're building complex codes. And they're critical in technical interviews because many times interviewers will ask you to implement an algorithm like a searching algorithm or a sorting algorithm or explain how they work in a certain context. So really useful for all these reasons. And now we're going to talk about algorithm complexity and Big O notation. So to understand algorithm complexity, algorithms are used to evaluate the efficiency, and that means really the resources that an algorithm consumes. And we can check that using two dimensions. So there's time complexity, which is how the execution time of an algorithm scales with input size. So you might want to know, I only have a certain amount of time to get this answer. And, maybe you can use time complexity to answer the question, can I get the answer in the time I have? And then space complexity is how the memory usage of an algorithm scales with its input size. So, and a lot of the times, another big constraint that we have in computer science is space. And you want to know, if I have a huge piece of data, how much space do I need to actually get the work done? So we will talk about Big O notation in this, which describes the upper bound of an algorithm's growth rate. And so it's a high level understanding of efficiency that we get by focusing on the most significant factors in the program. Okay. So here's some common Big O notations. O1 is super common. O1 means that the algorithm runs in constant time. When we have O1, it means that no matter how big our input is, the algorithm will run in the same amount of time. That is incredibly fast and basically the best outcome that you can get. O log n is the second best. It's logarithmic time. And linear time is ON. So linear time would mean that if you have twice as much data, it will take twice as long for the algorithm to run. Linear arithmetic time is n log n. This is a lot of sorting algorithms use n log n. And then n squared is quadratic time, which is pretty slow, honestly. It means that if your input is twice as large, then it will take 4 times as long to compute. Now that can get really long, really intense, really quickly. If you've ever seen a quadratic curve, they kind of shoot up. And exponential is the same way. So O2 to the n is exponential time. And again, you have a really shooting up steep curve. So that's pretty much one of the worst. There's also factorial time, which I'll type in the chat, is n exclamation point, but you won't typically ever have an algorithm that works with that. Ajax sent a really good link. Big O calculator. I'm going to visit this link on stream. Never seen this Vercel app, but that's seems like an awesome resource. Let's see. That's awesome. Thanks for sharing. So yeah, why don't we type in our first unique character algorithm that we wrote before. Let's see if it works to calculate it. I'm gonna need to delete these commas here, maybe. It seemed like it was giving some weird annotation to those. Well, all right, that wasn't working very well, but it might just be my computer, because my computer sometimes has issues with those features. But this is a great plot from that website that Ajax sent, just illustrating how steep some of those curves can be in the red. All right. So anyway, yeah, thank you for sending that. And we will continue on to have some examples of Big O, because sometimes people are like, what the heck is this Big O thing? Can we see an example? And I'm totally happy to show you some. So here's an example of a constant time O1 algorithm. A lot of people have trouble thinking, oh, what is an O1 algorithm? How could you have an algorithm that runs in the same amount of time, no matter how big the input? But a really good example is you have get the first element. So in an array, when you get the first element, it doesn't matter how big the array is, right? Think of it like when you take a drop of water, or let's say you take a drink of water. It doesn't matter if you take a drink of water from a cup or even from the ocean. I don't recommend taking a drink of water from the ocean, but it'll take you just as much time, right? Even though the ocean is so much bigger. And that's O1. And linear time is ON. So one example is printing all the elements of an array. So yeah, let's say that we have an array of, let's say, 100 characters. If we increase it suddenly to 200, then it doubles the time it takes to print, because this for loops typically run in n time, because they have to iterate through everything. So that is a great indicator that your algorithm has some n linear time complexity. And we also should talk about worst case versus average case when we're referring to Big O notation. So worst case complexity means the maximum time taken on any input of size n. So let's say we're looking through an array for an element, and we're trying to find the element number 3, and then just trying to find 3. Well, if 3 is at the way end of the array, that's the worst case scenario, right? Because we are going to look through every element in the array until we get to the end, and then finally find 3. Whereas average case complexity is the expected time taken over all the inputs of size n. So if we had a bunch of random number generated lists and we were looking for the number 3, that would probably be halfway on average through the list, right? Because it's going to randomly appear at some point in the list in each case. So then the average case complexity could be a little bit faster, a little bit less complex. And typically big O notation is calculated with worst case complexity. So we're going to do an interactive quiz now to kind of test your knowledge of this big O notation. And it's going to involve choosing a big O notation based on the algorithm I show you. So here's the algorithm. It's called sum pairs, and it's just going to sum every pair of numbers in an array. Okay, so we'll have I and J, these two loops, it'll iterate through, and they're just going to sum each other for every case. And does anybody have an answer for me on what the big O notation would be for this algorithm? See one response already in the chat, but feel free to think through it and let me know. Remember that a for loop indicates linear time complexity. And in this case, we actually have 2 for loops nested within each other. So that should give you some hint on how to solve this question. All right, so actually Malhar ND is correct. It's C, ON squared. I saw another vote for B, but really because we have 2 for loops, it's n times n. So, and it kind of makes sense when you think about summing pairs. So if the array is 2 objects, then you need to make 2 different pairs. That's going to be the first and the first and the last and the first, and the last and the last. So that would actually be 4 different pairs. But if you only had one number in each case, it would be only one pair. So when you double the number of elements, you actually quadruple the number of pairs. So that's a squared law. And yeah, why don't we now move on to sorting algorithms? And you might see how complexity, big O, and time complexity play out when we look at some of these sorting algorithms. So first, we're going to talk about an introduction to sorting algorithms and, what even are these things? So sorting algorithms are things that arrange elements of a list in a certain order. And it could typically be ascending order or descending order, but just some kind of order is all you need. And efficient sorting is crucial for optimizing other algorithms that, sometimes other algorithms are going to require sorted data. So in those cases, you really want to sort them first before you pass data as an argument to the function or the algorithm. So yeah, let's talk about some of the most common sorting algorithms that you might see. There's something called bubble sort, kind of a funny name, selection sort, insertion sort, merge sort, quick sort, and heap sort. And so we're going to focus on some of these today and actually implement them. But yeah, let's start with bubble sort. Actually, my personal favorite algorithm because I just like the name bubble sort. Bubble sort repeatedly steps through the list, and what it does is it compares the adjacent elements and it'll swap them if they are in the wrong order. And the largest unsorted element naturally bubbles up to its correct position in each pass. So you can tell that some of these are a little bit larger than others. So purple, for example, here is probably the largest number. And every time that the algorithm goes through, it compares purple to whatever's before it. Or I guess actually this is using gray as the largest one, this top one. So it bubbles down in this case. So it'll go down from red, swap with red, and then it swaps with orange, with yellow, green, turquoise, blue, purple, black, and then finally does not bubble past white. So that's an example. And then purple is kind of the opposite, where purple is quite a bit lighter, so it just sort of bubbles up to the top. And so you have kind of opposite behaviors of the two. And then there are some, like these green ones, where they kind of stay in the same place because they're sort of in the middle, and sometimes they get bubbled up, sometimes they get bubbled down. And so, yeah, this is how bubble sort works. And we can ask to optimize bubble sort. Can we optimize bubble sort to detect when the array is already sorted and stop early? So I want you all to try implementing a code that would detect when an array is already sorted and stop early. So why don't you think about that for a few minutes? All right, so you've had maybe a couple minutes now to look at this time complexity problem. And the goal here is not to optimize the worst case scenario. It's actually to optimize that average case. And so, sometimes we might see an array that is already sorted and we don't want to waste time bubbling. So we'll just want to immediately stop, right? And not waste any more time. So here's some common ideas. Maybe you could use a flag to check if any swaps were made in a pass. And if there's no swaps that occur, then the array is already sorted. So we'll introduce a swapped flag, and and into our bubble sort. So let's first write the bubble sort in a way. Let's write this function. Let me share my screen so that we can all check that. And I think I already put the unique characters in the code share. Let me double check that I did that so that you all have access. Yep, I put the first unique character function there. So I'm just going to delete it now so that we can clear out our code scratchpad. And we're going to build a new algorithm called bubble sort. So it's going to accept an array. And we're going to start by just saying n equals the length of the array. And we're going to create a loop. So this first loop is going to be for I in range of n. So that means it's going to step through, in other words, traverse the array. And we're going to say that for j in the range from 0 to n minus I minus 1. So now we're building a nested array that's going to check everything up to n minus I minus 1 index. And if the array j is greater than the array j plus 1, so in this case, you know, the previous element is bigger than the next one, then we're going to swap. So we'll say rj and rj plus 1 will swap. It's like that reverse string algorithm that we made earlier, only this time we're only interested in swapping if there's this inequality that gets satisfied. And then we will basically just return the array. So now our bubble sort algorithm is done. Should be anyway. So let's try making this. Yep, and when we give it some random list, it tends to sort it, which is great. All right, and so now we're going to add to this, but before we do, I want to put a little time, add a timer to this function. That didn't work. I forget how to add a system time. Yeah. So this is what we want. It takes 3 times 10 to the negative 5 seconds for this to run. What if the array was really big? Like let's make an array yeah. So this array has 1,000. Let's actually make even bigger. 100,000. That's a large array. And we're going to sort this array so that when we run this, it's going to sort it into 1, 2, 3, 4, 5, all the way through 100,000. I don't know if it's going to finish in a reasonable amount of time. Yeah, maybe I shouldn't have made it quite so big. 100,000, after all, is a really big array. You can see how long it's taking. Maybe we'll do just 1,000. All right. So 1,000 took 0.06 seconds to sort. And you can see it sorted from 0 all the way to 1,000. That's great. It never missed anything. But what if we gave it something that was already sorted, right? So instead of random array, I'm going to give it already sorted array. And we're just going to do the following. Actually, I think there was probably a better way. Yeah. So here's an already sorted array, okay? And so if we pass already sorted array, it still takes a long time, 0.01 seconds to complete. So we want to make an optimized bubble sort that will complete in less time. So we're going to call this bubble sort optimized, and we're going to add that swapped flag idea. Okay, so when we go into the code, first we'll add a flag at the very beginning of the for I in range n. We'll just say swapped equals false. And then we'll say that if we ever have a case where the preceding element is bigger than the subsequent, then swapped is going to be equal to true. So this flag is going to measure if we ever swap any elements when we go through that first time. And if we never get that to happen, then we can actually ask the array to exit early. So here's our conditional that will trigger after we go through that first pass. And if swapped was never changed to true, then it'll just break out of the loop, and we know the array is already sorted. So now if we run bubble sort optimized, so we'll call this sorted array version 2. And I want to first start with our random array and compare the performance of bubble sort and bubble sort optimized. So we're gonna put some timers on these and ask for the run times. So when we run this, sorted array runs in 0.01 seconds. And sorted array v2 runs in much less time. All right. And that's because, I guess we would have to redo this. That's because once this is done, it's already sorted out random array. So it just becomes so much faster. But if I were to re-randomize everything, and just like make a brand new random array for both cases, you can see it takes comparable time, right? But if we use, instead of random arrays, if we replace these with the already sorted arrays, then whereas the first one takes 0.01 seconds, similar to the random array, this v2 will take way less time. So we're not optimizing the worst case scenario when we do bubble sort optimized, but we are optimizing the average complexity of the algorithm. So that will let us save a lot of time if it is true indeed that our algorithm's already sorted and we can just stop early. Okay, so there are some benefits of optimization. By adding this flag, we just basically saved a lot of time, and we don't have to go through every pass possible and get our horrible n squared big O notation. And yeah, let's continue along to another sorting algorithm called selection sort. And I was afraid that this GIF would not work, and it seems like, unfortunately, I was right. But I'm gonna share my tab so that you all can see the selection sort tab. Let's try that. Just share my Chrome tab with all of you. And hopefully you can see now how this GIF works. So, oops, that's the next one. That's merge sort. So selection sort divides the array into a sorted and unsorted region, and it repeatedly selects the minimum element from the unsorted region and moves it to the end of the sorted region. So honestly, this is probably how I would do a sorting if I were a human. I mean, I am a human, but I think humans would most frequently use something similar to selection sort when we go through sorting some data, or sorting anything for that matter. We tend to just select the smallest thing and then select the next smallest thing and so on. But selection sort, unfortunately, also has a time complexity of O(n) squared. And that's because every time we find the minimum value in an array, it doesn't tell us anything about what the second smallest number is. So we have to traverse the array again. And that means a nested for loop, which is exactly what we're trying to avoid, but we do have that for selection sort. And then I think I have another GIF for merge sort. Yeah, I do. So I'll keep showing this this algorithm here. But yes, merge sort uses the divide and conquer strategy. So it recursively splits the array into halves until each subarray has one element. And then it merges the subarrays back together into a sorted order. So you can see that this GIF is running now. It has already split up the numbers into single elements, and now it's merging them back together. What it does is it's comparing the elements from each of these blocks and sorting them. So now it's comparing 1 and 2, and so then 3 and 2, 3 and 4, and so on, to essentially get those in line. So it's sort of a divide and conquer. And we'll go back to my slides because I don't really like how it looks to do that. But the key to the merge sort is this merge function that combines the two sorted arrays into one. Does anybody have any guess as to what the time complexity of merge sort is? Do you think that it's larger or smaller than O(n) squared? I'll show the GIF again so that you can see that. So the GIF let's see. So to split the numbers at the beginning, we do as many splits let's see, so there was 8, so we do 3 splits. So it's 2 cubed splits. And then every time we do a merge back together, there's 1, 2, 3, 4 merges because there's 8 units. So the merges are going to be going like n, because you need the number of merges you do is directly based on how many single units you end up with. But the splitting is where you save a lot of time, because you really see that the splitting is going to happen and just split them in 2 and be quite fast compared to n squared. Okay, so the time complexity is, like Malhar said, it's n log n. So the n comes from the merge part, and the log n comes from the split part. So merge sort is actually faster than bubble and selection sort. Okay, so we'll go back to our slides, and we're going to do a live implementation of merge sort. And to do this, we're going to go back to our Scratchpad. I think I've already put no, I actually have not put our bubble sort code into the share code share. So let me do that first. So our code share now has the hash map code. So I put the hash map code on line 1. The bubble sort code I'll put on line 20. And now we'll put on maybe line 40, let's just say. We'll put the code for merge sort. Okay. Oops. All right. So let's open up our Visual Studio Code. Delete all this stuff. Make a new code block. And we're going to start by defining a function, which we'll just call merge sort. And it'll accept some argument, ARR, array. And already gives us some suggestion, but we're going to walk through it step by step. So first, if the length of the array is bigger than 1, we're going to run this algorithm. This is another just check that you can add to your sorting algorithms. Because think about it, how could we split the array if it could only have 1 element, right? We just would be done. So we can find the mid of the array, the middle of the array. And so to do that, we're going to take the length of the array and we use the floor function to divide by 2. And that's going to make sure that even if it's an odd number, this length, it'll still split basically down the middle as possible. And we're going to divide the array elements into 2 halves now. Okay, based on this mid point. So the left half, we're going to call array colon mid. So that will just take everything from 0 index to the mid index, right just before the mid index. And then the right half will start at mid and will go all the way to the end. All right. And then we'll recursively sort the halves. So we're going to use this merge sort and just basically execute it again on the left and the right pieces, just like the GIF shows. So, you know, they'll split and they'll split and they'll split, just keep splitting. And then we will merge the sorted halves. So we're actually going to use some counter variables here. We're gonna say I equals j equals k equals 0. So we're just setting these counters to 0 first. And what we're going to do first is copy the data to temporary arrays, and we're going to call those left and right. Okay, so while I is less than the length of the left half, remember left half is this left split array, and j is less than the length of the right half, we're going to see if the left half is less than the right half element. And this is that part of the GIF where they're comparing individual elements from each split out grouping and seeing which one is bigger. And then in this case, the left half one is smaller, so it's going to actually be already sorted in a sense. So the next element is just going to be the left half one, and we'll increment that I counter, which is going to be our left side counter. And then if this is not the case, then we're going to add the right half element, all right? And just increment that as well. And k we're going to use to just keep track of this whole thing. So it'll just help us keep on track to make sure that there's no element left over at the end. So let's do that next, actually. So we're gonna check if any element was left. So while I is less than the length of the left half, we'll just say array k equals left half I, and increment both of these by 1. And then we'll say while j is less than the length of right half, we will say array k equals right half j. So we're populating the array with these values, and we'll do the same incrementing for that. And at the very end, of course, we will return the array itself. So again, we're implementing at the first our splitting. That's this whole first part here. And then we're going to copy the data into temporary left and right arrays for each case. And basically then put those into the array if there's any element left. Because we could have a case where we have odd sizes. And so when we have odd sizes, the split won't be even on each side. And we'll just need to accommodate that. So let's run this function and we can test it out. So let's test the function. So we can just make some random array. Let's just use this. And we'll print the sorted array and we'll see if it works. I'm just going to use merge sort. And it does. It gives us the array. What if it's an odd number? Well, it still works. No problem. Even though the list is 7 here, which is odd. Okay. So we've got our merge sort working. And basically, again, we recursively split the arrays until we got it down to a size of 1, and then we merged them back all together again. All right. And now we're going to talk about the time complexity. As I mentioned, it's O(n) log n, and as Malhar also did, and it's significantly more efficient than O(n) squared for large data sets. Okay, so just to prove that to you, why don't we check this out? So I'm going to keep my merge sort here. and I'm going to put bubble sort 2. Go back from my code share. Bubble sort was way more simple, if you'll recall. And I'm going to make this. So I have this random sample of data. It's called data. Let's see, I have 1,000 points. So we're going to run merge sort first on data. And then we're going to run, oops, that's not working very well. And then we're going to run bubble sort on data. So I'll just type merge sort done and bubble sort done. So that's not so bad, but let's try 10,000. So merge sort's done already, less than a second. But look, bubble sort is taking so long, right? Bubble sort takes basically 5 seconds. So you can see how much worse it is. And even if we do, let's say 100,000, I bet bubble sort will take forever. Merge sort took less than a second, but let's see if bubble sort ever gets done in any reasonable amount of time. We increased by a factor of 10. So we should increase our time complexity by a factor of about 100. So it should take 500 seconds or about 8 minutes for bubble sort to run. So we'll check back on bubble sort later. But yeah, that's it for merge sort. And now we're going to tackle quick sort. So quick sort is supposed to be basically really fast, just like merge sort. It's going to use a divide and conquer approach. And the way it works is that it's going to select a pivot element and partition the array so that elements less than the pivot are on the left and elements greater than the pivot are on the right. And then it's going to recursively apply that same logic to the subarrays after the split. Okay, so to choose a pivot, there's many strategies on how to do that. We can use the first element, last element, the random element in the array, and the median of 3, median of first, middle, and last. And these can be different pivots, could be useful for different types of data. It's going to really influence the time complexity of the algorithm, the average time complexity. So let's actually talk a little bit about what are the best case and worst case scenarios for quicksort. So this is sort of an interactive problem. And so what is the best case scenario? We could have the following. I'm going to type it in the chat. Best case scenario is O(n) log n when the pivot divides the array evenly. And so if that pivot is doing a super, good job in evenly divvying up the array, then n log n, we can get it just like merge sort. But the worst case would be O(n) squared, when the pivot results in highly unbalanced partitions, where we could have an already sorted array with a bad pivot selection, and then everything gets jumbled up and we're back to an O(n) squared situation. So that would be kind of the worst possibility. So to mitigate that worst case scenario, we can use the median of 3 point for pivot selection. So let's implement this algorithm. We're going to try that out. Wow. Bubble sort is still not done. So maybe while bubble sort's catching up, I'm going to put the merge sort in CodeShare. And on line 75, I'm going to put the quick sort, line 75 of the CodeShare, if anybody wants to check in and look at that. All right. So yeah, let's go ahead and basically, I'm just going to not wait, assuming that this will take another 5 minutes or so. It's not really worth it to us to finish the bubble sort. We get it. Bubble sort is slow, right? Okay. So we'll start this new function, quick sort. And it takes in an array and the two elements low and high. Because if you'll remember from the explanation of quicksort, it's going to select a pivot element and partition the array such that the element's less than the pivot on the left and the element's greater than the pivot on the right. So we're going to accept arguments based on that. And so, yeah, we can keep going here. So if the low is less than the high, the low is less than the high number, then we will do partitioning index. So we'll call that PI. Excuse me there. But we'll call that PI. And we'll say that PI is equal to the partition of array between low and high. And then we will separately sort the elements recursively using quicksort for each case. So in this case, we are taking the array and we are now sorting between low and the partition index, and then between the partition index and high. So this is how we're getting our pivot. And you might be asking, hey, Stephen, what about this error? We don't have a partition function yet. So let's make one. And it's going to take those same arguments that quicksort did, and we're going to use a median of 3 pivot selection, just like we talked about in the slides. So what that means is that we're going to take the mid of low plus high divided by 2, and we're going to basically then, we're going to have 3 pivot candidates. Get our pivot candidates. One of the pivot possibilities is the array at the low index. One of the possibilities is the array at the mid index, which is the median of the, this sort of mid point. And then one of the possibilities is the array at the high index for our pivot. Okay. And so then we'll say pivot equals sorted pivot candidates 1. And we're going to have to define that too. Actually, I'm a little bit confused about this sorted. I think maybe that just is a native Python. I guess I don't remember when I wrote that, what I meant by that. Yeah, I think it just returns a sorted list. So it's just going to modify the list in place using a really simple sort algorithm. Yeah, I can't really remember why I chose that, because it's not really, it's a native Python sorting when we're trying to look at sorting algorithms. But Regardless, that will tell us our pivot. Okay. So next we will get the pivot index. So get the index from the array of that pivot, and then we'll move pivot to the end. Okay, so what we're doing here now is just swapping the high with the pivot index, the high index with the pivot index. And so now we can say pivot equals r high. And we'll get the index of the smaller element. Okay, and so now we're going to iterate through all of the values from low to high, and we're going to say if the current element is smaller than or equal to the pivot, increment by 1 and swap them. And then we're going to swap the pivot element with the element at index I plus 1 and return I plus 1. Okay, so now I want you to test this function to see if it gives us the appropriate answer. And yeah, see if you can get that to work. All right, so hopefully this is working. Let's try it. Always a possibility in live code that you've mixed something up. So remember, we want to choose a high and a low number for our pivot. So when we do n minus 1 and 0, that's going to be basically all the possibilities. And then the midpoint of those will also be considered for our pivot. So, you know, it's a little bit slower than picking the ideal pivot right away, but we're not sure what that ideal pivot's going to be. So let's just try this. And if we type ARR now, it looks like, oh, I guess it didn't get fully sorted. Kind of strange. I wonder where we made a mistake here. Let's see. We had our pivot candidates and sorted those out. Interesting. I'll have to troubleshoot that one a little bit. Oh, I think, again, it could be a result of this not being quite right. Sometimes the tabbing on Python can give me trouble. Yeah, so at the end, we swap the pivot element with the element at index I plus 1, not during this list, which is where we're just swapping elements within a certain the low to high range. So, all right, that now works. And so I'll copy the quicksort code into the code share so that everybody has that. And again, it's about finding these partition indexes, finding these ideal pivots to essentially swap the elements, do sort of almost like a bubble sort that you would have for each of these smaller pivot subsets of the array. So the average time complexity is O n log n, but remember bubble sort and these other types of things, they can be n squared. So if the partitions are not very balanced, that's what you risk in quicksort. So definitely consider that. And for that reason, quicksort is a little bit poorly named, I guess, because really its maximum time complexity is much worse than merge sort. So you have to take that into consideration. All right, so now we're going to work on some searching algorithms, and this is sort of the second half here. So searching algorithms help us find the position of a target value within a data structure. And so linear search is the simplest of the searching algorithms, and how it works is that it sequentially checks each element of the list until a match is found or until the list ends. So it's really, you're basically just checking each and every single number one by one to find that. And as you can imagine, this would be kind of slow sometimes, because in the worst case, the element you're looking for is at the very end, right? We did talk about that from before. You might have to just deal with that fact, unfortunately. But there are some times where linear search is really the only thing we can do. And that's especially true for unsorted data. So, you know, we could have unsorted data and there's really nothing we can do. We have to check everything. And another case could be where where you have a small data set and the overhead of more complex algorithms is not justified, where you don't really need to have a complex search algorithm if you just have like 100 entries and you're looking for you're searching every few times a day. But you really don't need something that's going to be super complex. Then there's also binary search, which is a bit more efficient for searching in sorted arrays. And here's some concepts for you to remember when you think about binary search. So it starts by comparing the target value to the middle element of the array. Now remember, this is assuming that the array is sorted, so the middle element of the array is actually the median value. And everything to the left of that median value is smaller. Everything to the right is larger. And if the target is not equal to this middle element, then it'll decide whether to continue the search in the left half or the right half. And it'll repeat that process, effectively having the search space each time. So this is really similar to, remember, merge sort, where we split the data iteratively to save time. Saved a lot of time to do that compared to checking every single pair. And, that was great, but there is one precondition to remember, and it's that binary search can only work correctly if the data is already sorted. So if the data is unsorted, unfortunately, we're stuck with linear search. And so I want us to now check an interactive problem where we implement binary search. And I actually think it's okay. I have here implement both iterative and recursive versions of binary search. I think it'd be great if you can get either one to work. So don't worry about doing both, but I am going to walk along too with this code for binary search. And I think I'm going to start with the iterative version. Wow, it already knows that we're going to do binary search. So we'll have two arguments that we pass into binary search. It's the array, which is, it has to be a sorted array. We could do a Python list, sorted Python list. And the target, which is whichever number that we're searching for. And because this is an iterative approach, we're going to need some pointers. So we're going to do left and right equals 0, and the length of the array minus 1. So these are just going to be those upper and lower bound indexes. And while the left is less than or equal to the right, so in other words, while that left pointer's on in its appropriate orientation, we'll calculate the midpoint. And you might remember that we have the left plus, I actually want to just write plus right. I don't want to do right minus left. And divide by 2. So that's how we calculate the midpoint, or the average of two numbers. And then we can say if that array mid is equal to the target, then we'll return mid. And we basically found our target then. But that's not so likely, right? The most likely thing is that we didn't. So then if the number is less than the target, that means we want to increment the left by 1. So we're going to shift up that left pointer to make it so that we're now looking at the upper half of the data, of the remaining data. And then we'll use else to indicate that the right pointer could be shifted over to the lower half if this is true, if the opposite of this is true, where array of mid is greater than the target. Okay, and then if nothing works, we'll just return -1 to indicate that the target was not found. So that's our binary search. And we can even test this out. So remember, we need a sorted array. So we can use the following: 1, 3, 5, 7, 9. And let's make our target 5. So when we search for 5, we should see that 2 comes up. That would be the index of 5. And indeed, we get it. And we can change that to any number and get the appropriate index. But there's another way to do binary search, and that's with recursion. So we're going to call this one binary search recursion. And I'll use array and target. And we're actually going to use left and right also, okay, for this one. And those are going to be our pointers, because we're going to need to pass in the pointers every time we use the recursion algorithm. So if the left pointer is bigger than the right, of course, then we return -1, because it means that we went through the entire array and we never came across that target. But if we don't see that, then we're going to calculate the midpoint. So we'll do left plus right divided by 2, mid, and then if the array mid equals target, we'll return mid, and otherwise we'll return mid less than target. We'll return the binary search recursion again. And so we'll just update that. And remember, we need to restrict the pointers to the lower half or the upper half, depending on which side of the target our midpoint is. And we could test this function out again. We'll just copy our code from last time, but this time we'll call the function recursion. Oh, that's right. We need to pass in some original arguments for these left and right pointers. And you can see that it works. So that's the example for recursion. And yeah, that's another way just to get this going. And you might be wondering, what is the time complexity of binary search? It's log n, which makes it really efficient for large data sets. And you'll probably remember from our part one, or not part one, but from our merge sort conversation, you'll remember that merge sort was log n because it only relied on 2 to the x number of splits for some amount of data. So it was logarithmic. And binary search also works on splitting the data, but there's no recombining everything. So instead of n log n, it's just purely log n. And so that makes it really efficient for large data sets. I think actually binary search would be the fastest algorithm we have discussed today. And so we have another interactive problem, but before we do that, I want to paste in our code for the binary search. So I'm going to put the binary search code in line 105 here. And so you can try those on your own. And I'll even put an example at the bottom, some examples for you. All right, so now that code is into the code share, we can actually do another interactive problem. And this time, what the interactive problem is it's to modify the binary search algorithm, and we're going to find the first occurrence of a target value in a sorted array that may contain duplicates. So in our first example, we did not really consider the possibility that there could be duplicate values in the list. And so now we're going to do that. We're going to consider that explicitly. So if you go back to our code, we could adjust the algorithm to continue searching in the left half even after we find the target. So that might be a way to adjust this algorithm. And so I'm going to make a function called first occurrence. That's going to have an array and a target as arguments. And we're going to do the same exact thing that we did for binary search, where we had some left and right pointers. But we are going to use this result variable, which is going to keep that midpoint. And while the left is less than or equal to the right, so while these pointers are oriented correctly, we'll just calculate the midpoint. And if that array at the midpoint is equal to the target, then we'll set the result variable, which we're tracking these results, to mid. And we will put right just to the left of mid, so that we can continue the search on the left side. If we have a case where array mid is less than the target, though, then we will put the left equals mid plus 1, and else we'll do right equals mid minus 1, just like we did before, but we're going to return result at the end now. Because we're checking this, we're going to keep searching on the left side to see if we can find the first occurrence. That's really the key difference here. And so we can test the function. I built a little test code for it. And we get first occurrence of 2 equal to 1. All right. So I'll put this in 2. And Akshat says, wouldn't it be easier to use linear search for this kind of problem? You know, it could be, but linear search has n time complexity, remember. So n is actually quite a bit larger than log n for large data sets. So in this type of problem, we have a small data set of just about 7 numbers, but with linear search, it'll get really slow when we have, let's say, 100,000 numbers. So that's a good question, but I would think binary search will be faster. And so we did a little bit of live coding, and we're going to do algorithm design techniques, but I'll just give us about a 1-minute break to ask some questions, absorb some of this material, and just allow me to quickly post some of this in the code share. All right, everybody. So we're back. The codes are in CodeShare, so we can move on to the next thing, which is going to be some algorithm design techniques. And I want to, of course, emphasize that the essential algorithms are, well, they're essential. You want to know about quicksort, merge sort, binary search, if you're going to do anything with data structures and algorithms. But you know, knowing how these algorithms are designed is important too. Okay, so one algorithm design technique is called greedy algorithms, where you make the locally optimal choice at every step. And your hope is that you'll find a global optimum by doing this. It, of course, does not reconsider choices once they're made. So once you make that locally optimal choice, it's time to move to the next step. And they're not always optimal, but they often produce a good solution for certain types of problems. So greedy algorithms is one legitimate way to do things. And then here's an interactive problem. So we could say, okay, we want to make an algorithm that selects an activity. So if we're given a set of activities with start and finish times, we want to select the maximum number of activities. So we can do the maximum number of activities, but we don't choose anything that overlaps. So I want you all to think about this problem. And if you think of a way to solve it, say so in the chat, and then we'll walk through together. So I'll give you a few minutes to look at this one. Okay, so the answer here is that we're going to sort the activities by their finish times, and we'll always pick the activity that finishes the earliest. All right, so let's try to implement that in code. Delete some of these. And so we'll say activity selection is our function. And we'll give some activities, which will each, they'll have a start and an end time. And we want to first sort the activities by their finish time. So I'll say sorted activities equals sorted, which is the Python sorting method. And we'll just sort by the finish times, which are the element ones here of each of the sorted activity pairs of start and end times. And then I'm going to make a selected activities empty list here at a last finish time, which I'll say is equal to 0. And then for every activity in sorted activities, if the start time is greater than or equal to the last finish time, then we can add that in. And by the end, we'll return the selected activities. So we're just going to basically see whichever things finish earliest. And we will always pick that activity and just keep going through. So even though this might not actually give us the most globally optimal way of picking our activities, at least it'll be a good way to pick them efficiently. All right. And I have another example for you to check, which is called divide and conquer. So this is where we break the problem into smaller subproblems. We solve each subproblem independently, and then we combine their solutions. So that's what we were doing with our merge sort, our quick sort, and our binary search. We broke things up by splitting them. In the case of merge sort, we split along the middle. In the case of quick sort, we split along some partitioning index, some pivot. And in the case of binary search, we went ahead and split that way too. And some of the benefits of divide and conquer are that they can reduce complex programs into simpler ones, and that they can often give us a more efficient algorithm with a logarithmic time complexity, because remember, these splittings, they're typically logarithmic in nature. And there's one more category I want to speak about, which is dynamic programming. And I'm not going to get too far into the weeds with dynamic programming yet, but essentially dynamic programming is a method for solving complex problems by breaking them down into overlapping subproblems and storing their solutions. So the idea here is that we might be able to find some optimal substructure such that the optimal solution is constructed from the optimal solutions of subproblems. And overlapping subproblems means that subproblems could recur multiple times throughout the code. So some famous examples of dynamic programming problems are the Fibonacci sequence, where you do have overlapping subproblems. And then the shortest path algorithm, for example, is another one that people know, to find the shortest path in some kind of graph. So those are some examples. In our next workshop, we're going to dive deeper into into dynamic programming and some more advanced concepts like this. So if you're interested in learning more about some of these concepts, stick around for part 3, where we're going to dive really deep into those. And yeah, that pretty much ends things. So we're going to have a summary. If anyone has any questions, also, this is a great time to ask them. But while I'll wait for any questions to trickle in, I'll give a summary of what we did today. So first we talked about hash maps actually, and hash tables. But then we moved into the part 2 content, which was sorting algorithms like bubble sort, selection sort, merge sort, and quick sort. We then covered some of these search algorithms like linear search and binary search. And then we got into algorithm design techniques, where we learned about greedy algorithms and the divide and conquer approach, and some intros to dynamic programming. But yeah, I didn't see too many questions in the chat, so maybe we'll just end it for today. We've been going over a lot of this stuff today, so I understand if people have done a lot of it, but Aziman is going to be leading another workshop called Garctic Phone Mini Event. That's going to be really fun. This is in Discord, and it's taking place at 10 p.m. Eastern Time. So let me put that in. Sounds like a lot of fun, and I think if you're interested in sticking around for some more Global Hack Week content after this, check out Aziman's stream. And then later today, UT is going to do some more mobile app development with React. So if you are interested in that too, check it out. But all right, everybody, I'll talk to you next time. See you later.